Great, thanks very much. How do I get it on?
Yeah, that's nice.
Okay. So I come from Bristol, but I notice every time I come here up the hill, I take about 5 seconds longer. So it's a depressing place to come and speak for me. Yeah, I'm going to talk about strengthening causal inference in epidemiological studies through the use of triangulation of evidence, and I'll explain what, hopefully show what I mean by triangulation of evidence as I go through the talk. So triangulation, as I'll be talking about it, is to improve understanding of causal relationships within data so that you can actually decide on what things you could actually intervene or act upon that would actually have some effect. I mean, the reason for why one would want to triangulate evidence is because of some rather spectacular examples of impactful interventions which were based upon evidence which turned out to be not to be reliable. I've got some examples from the neonatal field, but some examples are from areas I've worked in, which aren't neonatal, but hopefully the methodological connotations remain. So these were some studies from a long time ago. Two back-to-back papers were published in the New England Journal of Medicine, looking at people using vitamin E supplements in 2 very large observational studies, nutritional studies in the US. The exposure was people who reported taking vitamin E supplements. So the exposure was a specific and identifiable exposure. Taking vitamin E supplements in both the Nurses' Health Study, women, and the Health Professionals Follow-Up Study was associated with 35% lower risk of coronary heart disease occurring in the subsequent, in the follow-up period. This was reported, this got to the front page of the New York Times and was reported as saying vitamin E greatly reduces the risk of heart disease, studies suggest. So, causal claim, vitamin E reduced heart disease risk. Not surprisingly, when you stratified by the length of follow-up, you're seeing this benefit in about 2 to 4 years of taking vitamin E. You're seeing the sort of full apparent benefit. People are sensible, so when they read the New York Times, they actually start taking the supplements. You see vitamin E supplement use going up between 1992 and 2000. And the multivitamins contain vitamin E, and about nearly 50% of the US adults were taking vitamin E supplements at one time. There was a very rapid growth in vitamin E supplements. The people in the studies, the Nurses' Health Study, they started taking vitamin E, went up from 15% to 45%. Of them were taking vitamin E supplements. And the increase came from that after 1993. These results got widely disseminated, and they were impactful. And same seen in the other study. Of course, the denouement was then large-scale randomized controlled trials were set up, which tested precisely the same exposure, which is taking vitamin E supplements for a few years. But these trials went up to 10 years of follow-up. And taking vitamin E supplements are doing precisely the same thing in the randomized controlled trials had absolutely no beneficial effect. And yet there was a large portion of the population were doing something which was having no beneficial effect. And people being clever, once the trials appeared, I mean, these are health professionals, they stopped taking vitamin E supplements. But also when they stop taking vitamin E supplements, they'll also think about be skeptical about medical advice. I mean, these constant claims of things being beneficial, they don't have neutral effects. They lead to disenchantment. Now, here's another sort of interesting thing. Here we see beta carotene levels going up in the Health Professionals Follow-Up Study, and these beta carotene. The beta carotene was going up because of news reports of a conference presentation from the same studies. The same studies showed the same thing, that apparently beta carotene levels intake was associated with lower risk. And the people were starting they were reported at conferences at the same time, and the conferences got publicized. People started taking beta-carotene supplements, but you notice there's a drop in the beta-carotene supplements. Occurs earlier than the vitamin E supplements. And that is because the first trials started appearing showing that beta-carotene, if anything, was increasing the risk of lung cancer in smokers and was certainly not reducing the risk of coronary heart disease. I mean, beta-carotene might have been harmful. Now, these papers never appeared. The papers on beta-carotene never appeared because the trials came out. If the trials hadn't come out, you would have had 2 New England Journal of Medicine papers saying beta-carotene, about beta-carotene. So these are quite impactful on epidemiology, certainly, in thinking about what you need, what you can actually do with observational data. The fact that you can't statistically adjust for differences. The lesson is these studies had lots and lots of covariates. They did all the adjustments, everything, but the results were incredibly robust. You get very robust associations which have no causal significance. And in the neonatal field, there was observational studies showing that vitamin C levels intake during pregnancy was associated with higher birth weight, and randomized trials showing, if anything, lower birth weight with vitamin C supplementation. So these same pictures are seen. So the basis of triangulation of evidence comes from in the sort of in causal inference terminology, what's called the variety of evidence thesis. And this means that it is not the volume of evidence that matters. It is the difference in the source of that evidence and the difference in the biases that will exist in studies. So the volume of data generated from similarly biased sources rapidly asymptotes in value. You know, we showed that the vitamin E results replicated, and if you had 100 other studies in the same sorts of populations with the same compounding, they would have replicated in those as well. And so, in fact, just the volume of data can become detrimental because it makes things look extremely robust. And here we see with beta-carotene, this is a sort of meta-analysis of the cohort studies all showing protection, and then the randomized trials showing, if anything, adverse effects. Now, the interesting thing is, as I said, these cohort studies stopped appearing. Once the trials came out, no one was going to publish a paper saying beta-carotene associates in these observational studies with lower risk of all these diseases. It still does, but there's loads of trials, so no one is publishing it. And the point is, with observational data, you can deal with the observational data in lots of different ways. This is a recent study I really like. It's from the the social sciences field, and this was a data set looking at an issue which is completely unresolved in social science relating to social attitudes and migration. And the data set was prepared and given to 73 independent research groups. They were not given any hypothesis or whatever. They were just told they were to examine this issue. And what you found here is, with exactly the same data, you had 25% of the groups were saying they were statistically significant. This is a term that should never be used. You should ban the use of statistical significance as a term in all publications, to show an association in one direction, and 17% and the association in the other direction. There's a tendency that you want to find something when you're analysing data, and so 57% found it in the point estimate, which wasn't significant. So analysing data, you can analysing data in different ways can lead to different findings. So it's the variety of evidence involving different methods and domains of data that's key. Now, you can use intuitive and formal reasoning regarding whether the biases in the different study designs would be expected to point in the same direction, in opposite directions, and what the magnitude of the biases might be across study designs. Establishing mechanisms linking exposures and outcomes definitely strengthens evidence of causation. And quantification also adds to the evidence, but is not essential. There's been some beautiful examples historically in causal inference in the medical sciences for which there is no quantification. So I'm going to discuss a few varieties of evidence that can be used in epidemiological studies. So there's conventional observational studies, like the vitamin E studies, beta carotene studies, etc. They are probably of the lowest level of information. What you can do when you have a situation where you have a good hypothesis about what is driving the confounding within studies is you can think about getting studies in different contexts where the confounding will be in opposite directions. Now, one of the most confounded associations that there is that between breastfeeding and outcomes. You'll all know that having been breastfed has been reported to be associated with everything which is good. And in Alsbach, which I guess most of you will know of, in Bristol, set up by Jean Golding, in Alsbach, breastfeeding was very strongly associated with higher levels of maternal education, greater household income, etc. So breastfeeding was what was confounded in a way which you'd expect to lead to associations in the sort of beneficial direction. But I mean, but what one is interested in would be the biological effects, whether that is the biological effects of being held close or the biological effects of breast milk or whatever. You would think that there would be some actual effects, but the higher socioeconomic position would generate many outcomes that would become associated with breastfeeding. Of course, this is what is seen. So now there are two set of birth cohorts were set up in South Brazil in Pelotas that we've worked very closely with over many decades. And in Pelotas in 1982, when the first birth cohort was set up, breastfeeding was patterned in, if anything, an opposite direction, socially patterned in an opposite direction to Alsbach. So here we have the percent ever breastfed and the percent breastfed for a certain period of time, showing the very strong positive association with income in Alsbach and certainly not a strong positive effect of anything, negative association in Pelotas. And this is the odds ratios for breastfeeding by social class, paternal and maternal education, and by income, showing the big difference between Pelotas and Alsbach. And in Alsbach, of course, breastfeeding was associated with lower birth weight, with lower body mass index. There were many meta-analyses, which I was involved in some of. It's incredibly robust association, the breastfeeding, and then lower body mass index in children, in the children, and with higher IQ. You'll see in Pelotas, they did not show these associations with blood pressure or with BMI. If anything, the BMI association was in the opposite direction. So that would suggest that when you're looking at these associations that you would expect to be the same if they're biologically driven, suggests that the context matters, which means that they are unlikely to be invariant causal effects. But interestingly, the cognitive ability was positively related in both studies. Pelotas is quite small, but there is a consortium of birth cohorts in low and middle income countries called the Cohorts Consortium. And the Cohorts Consortium produced data on these same outcomes. And you see here, you can now see robust differences between the Alsbach and the Cohort Consortium associations, suggesting they're non-causal. Sadly, Pelotas was the only study which had reasonable cognitive function data. But there's also been a randomized controlled trial of this one reasonable randomized controlled trial of breastfeeding, which was a cluster randomized trial of hospitals in Belarus which when Mike Kramer set this trial up, was one of the places with the lowest breastfeeding rates in the world. And the hospitals were randomized, the 31 hospitals were randomized to either promote breastfeeding or just to have usual care. And they generated a substantial difference in breastfeeding. And Richard Martin, who's the current head of population health sciences here, and at the time was a PhD student of mine, became involved with Michael Kramer in following up that trial, the Belarus trial. It was set up for short-term outcomes, but then they've now been followed up to about age 18. And so we can compare these observational associations with associations from randomized evidence. And the randomized trial evidence showed no effects on blood pressure or BMI, but did show an effect on cognitive ability. So here you have a cross-context comparison which threw doubt upon the blood pressure and body mass index associations. And then that is backed up with another variety of evidence, which would be orthogonal, any biases. Randomized trials can be biased, but the biases which the confounding which generates the associations in ALSPAC will not be a form of bias that would be reproduced within a randomized controlled trial setting. This is my favorite cross-context comparison of all. Fried food, everyone knows, you read the newspapers, fried food kills you. Fried food is absolutely terrible, terrible. Now, these are studies from the US, or of course, the Nurses Health Study, the same studies generate these data. You see the headlines on this all the time. Your context can be time. Go back 60 years in the US. Fried food was then eaten, if anything, by better off people because it was steak, meat that's what you slapped in the pan. This is my favorite epidemiological finding of all time. This is the number of times you have fried food per week and your mortality stratified by smoking. What I love, it carries on going down between 14 and 15 plus times a week. You cannot get enough fried food to live longer. Hugely robust. Statistical significance, you don't need to do a bloody calculation on this. So, I don't think fried food makes you live longer, but nor do I think fried food is as terrible as it's portrayed now, because it is confounded, it is just totally confounded by socioeconomic position, other health-related behaviours, etc., etc. So, yeah, that's it. So that's cross-context comparison can be a really powerful approach. So another variety of evidence, which is negative controls. So negative controls are either when you have an outcome which is implausibly causally related to your exposure, or you have another exposure which would match your exposure of interest, but will be confounded in the same manner. Those are the negative controls you can use. And in the breastfeeding example, I think Deborah Lawler has published some data on this, but certainly if you do the analysis, you see it. You see breastfeeding influencing lots of things which are implausible. Cannot be caused by it, like the size of Christmas presents you get, for example, things like that. And if you do exactly the same analysis, you adjust for all the same covariates, you get just as robust p-values with these negative controls. But it does throw doubt on the things you see. The first negative control study I was involved in was on smoking and suicide, because in the late 80s, a whole stack of papers came out saying smoking had this very large effect on suicide. And we replicated this in a study of a third of a million men in the US, the Mr. Fit study. And sure enough, you get this very strong dose-response association between smoking and suicide. And of course, you could have biologically plausible reasons. Serotonin, all you have to do was mention serotonin. Smoking has an effect on that. Leads to people being depressed. The other possibility is that people who are depressed find it very difficult to give up smoking, or people are self-medicating with smoking for depression, etc. So I thought, well, what is smoking implausibly related to? And this is the US. It's implausibly related to being shot dead. And being the US, there's enough deaths from homicide to show that smoking was as strongly related to being murdered as it was to suicide. But I thought it was rather implausible to have a causal model for that. The only one I could think of was that the paramilitary wing of the Health Education Authority were going around shooting smokers. That's the only way smoking could be related to being murdered. Or going back to our fried food example, there's the thing you'll see a lot of headlines about at the moment, if you haven't heard this terminology, you will do, is the ultra-processed food. So this is the new poison. This is like, it's ultra-processed food, and it relates to many things. And one of my current brilliant PhD students, Fernanda Morales-Bernstein, has been working on this in head and neck cancer. And sure enough, you see that ultra-processed food in these models, adjusting for different potential confounding factors. It's related to head and neck cancer, but it's also related to accidental deaths, which is not a plausible association. Now, in the sort of neonatal relevant field, rather than negative control outcomes, although some work has been done with those, there's been a very common use of negative control exposures to look at exposures during pregnancy that are thought to have a biological intrauterine effect. And the negative control there is provided by the dad, because what the dad is doing will not have the same will obviously not have the intrauterine effect of what the mum's doing. Whatever you think about how bad passive smoking is, what the father's, the markers you get for smoking, if you live with the heaviest smoker in the world, is less than that of about a third of a cigarette a day. So there's not this is not going to have the same. It's going to have orders of magnitude lower intrauterine effect. So and here sort of the proof of principle example is that in Alsbach, maternal smoking is related to offspring birth rate. The dad's smoking is related weakly to that, but there is some assortative mating by smoking. Of course, smokers mate with smokers, and when you take that into account, there's no association of father smoking. So that's what a causal effect looks like. Again, the newspapers used to be full of it saying that maternal smoking is very bad. I'm not saying it's not very bad, but it's been said again to cause everything, including obesity in kids. And indeed, there's a very strong and totally replicable in high-income country, massively replicable association that if you're an offspring of your mother who smoked, then your kids tend to be more obese. But the association's the same with dads smoking. My mum was a 2-pack-a-day smoker, and when I told her I was working on these issues when she was still alive 30 years ago when I started, she said, "Sue me." And I thought it was a great response. And I thought it was a joke, and it was a joke. In the US, currently in the US, there are cases of children suing their mothers for smoking and drinking during pregnancy. My mum was a Guinness fan as well, so I was bathed in nicotine and Guinness. That's why I'm sort of epidemiologist in the provinces rather than being a neonatologist or something more prestigious. So yes, and so these have been used a lot. My favourite one that I was involved in on this is I've worked in India for a month a year since 1992, etc. in the pandemic, is on parental height and child mortality in India. And you see that the taller the mothers, the lower the childhood mortality. And I thought this was likely to be socioeconomic, but the paternal height is not related to very weakly related to the childhood mortality. And that's both in the same model. So that suggests there might be something in that association. And the earliest sort of negative control that I know of in the neonatology field was by the genius of Lionel Penrose, whose work is really worth reading. But he used just maternal age in relation to Down syndrome, showed a strong relationship with maternal age. Once that's taken into account, no associative mating taken into account, no association with paternal age. Other examples of getting evidence, stronger evidence than the conventional observational study, is within sibling studies, where you have the control is obviously your sibling who will share the same family background, will share the same mother, etc. This is a quite widely used approach. Regression discontinuity as a form of natural experiment. This is a recent one in the neonatal field, used a change in alcohol prices in Finland in the early 2000s, when the cost of alcohol went down quite dramatically just on a day in Finland through a change in the law, because it's very highly regulated, alcohol sales in Finland, because of EU legislation, meaning that the Estonian cheap alcohol was being brought in huge amounts, so they changed the alcohol price to make it cheaper. Alcohol consumption went up about 10%, and the regression discontinuity on congenital malformations and on the abortion rate both showed a sort of change around this point. I get my favourite regression discontinuity is the one on coronary artery bypass graft, and mortality. Guidelines in the US, but basically pinpoint 80 as the sort of time before. Under 80, you do everything you can, stenting and whatever, and after 80, that is less automatic. And you see, if you're going to get admitted in the US for stenting, just tell him you're 79. This is what this tells you, because so what you're showing here is the people who were admitted 2 weeks before or 2 weeks after their birthday, and if you there's just a big drop in actually getting coronary artery bypass graft. This is bypass graft, not stenting. When you become 80, they're just it's no longer in the hospital guidelines. It's really quite dramatic. Again, quite dramatic effect. So lie about your age. Well, none of you are even approaching it, but I'm beginning to think about if I go to the US. Anyway, then there's Mendelian randomization, and I'm not going to say much about that because Kin Yang is giving a talk tomorrow, which is going to be on Mendelian randomization. So, but what I am going to do is I'm going to show I'm going to show a brief YouTube video. And it's only 2 minutes, and I want everyone to get their kids to watch this from every computer they go to watch it, as long as it's a different IP address, because it's had 80-something thousand views, and if I get 100,000 views, then I earn about a penny or something for a year. So I'm set to become I'm not going to be a YouTube millionaire, but there you go. Epidemiologists are interested in understanding factors related to health and disease. Do smokers tend to die younger than non-smokers? It certainly looks that way, but disentangling cause and effect can be difficult. Smokers are different on average from non-smokers. They're more likely to drink heavily and have less healthy diets. But even if we measure these confounding factors, we may not measure them perfectly, or there may be others we haven't measured. Also, as people become ill, they may cut down or give up smoking, which could wrongly suggest that reduced smoking leads to worse health. We could randomly assign 50,000 people to smoke and 50,000 people to not smoke and follow them up to monitor their health. This removes the possibility that any other factor could be responsible for any differences we see in their long-term health. But this is neither ethical nor practical. Fortunately, we've all been recruited into an experiment without knowing it at the point at which we were conceived. Our genes, which are passed on randomly from generation to generation, influence how much we eat, sleep, drink, smoke, and more. These genetic influences are not affected by anything else you may or may not choose to do in your life. They're not related to confounding factors. We can use this knowledge to learn about cause and effect, grouping people according to their genetic code. This method is called Mendelian randomization. For example, smokers who carry one version of a gene called CHRNA5 tend to smoke less heavily than those who carry a different version. When we group people according to which version of this gene they have, we find that the people with the version of the gene associated with heavier smoking do indeed die younger. But is the gene influencing how long we live in some other way? We don't think so. When we look at the same gene in non-smokers, there's no effect on life expectancy. So the effect must be driven by smoking. Using this method, we can show that smoking causes lung cancer, heart and respiratory disease, and many other diseases, but does not seem to influence depression or anxiety. Mendelian randomization has already begun to tell us about factors that influence our risk of disease. Now we're using the same approach in other ways to look at several risk factors together and to look at what influences disease progression, which may help us to develop new treatments. There we go. I don't know what I have to do to get onto the next slide now. Perfect. Thanks very much. Yeah, so this is just a schema for Mendelian randomization. In randomized trial, the experimenter randomizes people in Mendelian, and then your analysis has to, of course, be intention to treat. It has to be the group you're randomized into. In Mendelian randomization, if it's again an intention to treat analysis, you get the random segregation and distribution of alleles. We introduced the notion as a between sibling design, but in 2001, when I first mentioned this, there was just no large scale studies of hundreds of thousands of siblings you could look at, but now they are, and so you can do between sibling when it is really truly randomized according to Mendel's laws, and you just analyze by the allele that the person has, and you know that allele on average has an on average difference in phenotype. And this approach can be used to look at the effects of, for example, intrauterine environment on offspring outcomes. And I think Kunyang is going to talk about some of these examples. In fact, in the first paper we published, Sharibam and I published on Mendelian randomization, one of our pin-up examples was maternal folate and neural tube defects, because if your mother carried a -677 MTHFR variant, which could be taken to be like lower folate activity, then you have twice the risk of a neural tube defect. If your father carries the allele, there's no influence, because it's obviously intrauterine folate that matters. You can use genetics to estimate the confounding, as well as doing Mendelian randomization, where you actually estimate the causal effect by using the genetic variant phenotype associations. You can also look at what factors cause your exposure, and and if you see that educational level causes or influences exposure, then you'll know that it's confounded. So you can use genetics to estimate the extent of confounding. And you can also examine genetic confounding, because another possibility of associations you see is that it's the genes which are driving the association. And a beautiful example of this, I think, is by Rice and Thapa, who looked at artificial reproduction, where there'll be a division between who provides the ova and who provides the womb, and quite often the womb provider will be related to the ova provider, and other cases not. And so they got large enough numbers to be able to then look at the association between prenatal smoking amongst the mothers and the offspring antisocial behavior. As I say, mother smoking has been to cause everything, and what you see is that in the related pregnancy, so where we usually be sister, where there's sort of 50% genetic sharing, you did see such an association. But in the unrelated pregnancy, where the womb provider was not related genetically to the offspring, there's no association. So this suggests that the association is driven by the genetic influences. And if you look at scores for things like attention deficit, genetic scores for attention deficit, antisocial behavior in particular, they relate quite strongly to smoking. So that's I think a lovely design. You can Mendelian randomization. The genetic variables are sometimes referred to as instrumental variables because they associate with your exposure, but they wouldn't relate in any other way to your outcome. You can use non-genetic instrumental variables like well, I'll get on to one example of that. And obviously RCTs but often they can't be done. Now, as a sort of proof of principle example, if you look at maternal smoking and birth weight of offspring, you have conventional observational studies, but you have cross-contextual comparisons. You have places where smoking is, in some in low-income countries, sometimes positively socially patterned, etc. However, smoking is confounded. In the context, it still relates to offspring birth weight. You have negative controls. I've shown that. You have within SIBSHIP. The SIBSHIP can be the mothers. To mothers, sisters, pair of sisters, one who smokes, or the SIBSHIP can be the same mother but having two offspring where she smoked during one pregnancy and not during another. So you match on lots of factors. Those show it. Children of MZ twins is the ultimate between SIBs, I guess, because there's no genetic difference. And between MZ twins, when one smokes and the other doesn't smoke during their pregnancies, there's a difference. There's difference you see. Mendelian randomization. The video mentioned CRUNA5, this variant that leads to you smoking more heavily. If the mothers are smokers, and therefore the variant should relate to more exposure, you see that it relates to lower birth weight. If the mothers are not smokers, the variant is irrelevant because it relates to heaviness of smoking amongst smokers, not taking up smoking. So all these different methods, and there are randomized controlled trials. There's also in the Thapar and Rice paradigm, you see the same thing there. You see it in related and unrelated pregnancies. You see the relationship between the mother smoking and the offspring birth weight. So in that situation, it's not genetic confounding. And there's randomized controlled trials. There's only a couple of very small randomized controlled trials, but that's what a cause looks like. So an important issue is that the biases are independent. So technically, this can be framed technically as saying that if you had a large number of one study type, say randomized trials, and a large number of another, say Mendelian randomization or negative control studies, the results from one set would not predict the direction and magnitude of the association in the other set beyond causal effects. So that it can in principle be tested. In principle, it could be tested. So once you've got your different sets of evidence, what do you do with them? Well, one thing is you have to think, what are you actually trying to estimate? What is the causal effect you're trying to estimate in precise terms? So, for example, are you trying to estimate the effect of a statin for 5 years, or a difference in cholesterol level for 5 years? That's what you actually want to know, what lowering cholesterol for 5 years would do. Or would you want to look at lifetime effects? Examples of where you've got different estimans would be Mendelian randomization studies and trials. In trials, say of statins, you give them to people for five years, and the randomized trials, the genes relate to your cholesterol level from birth on in Alspach. Genetic variants relate to your cholesterol level from very early on in life. What you see is that you see in the Mendelian randomization studies, your effect estimates are about 2.5 times as large, i.e. the beneficial effect of a particular difference in cholesterol is larger because this is a lifetime difference in cholesterol, which obviously would generate a larger difference in the disease rate. For 5 years, produces about 40% of what you would get for a lifetime difference. But then you can scale these and then combine them. So if you know how to scale your estimans so they agree, you can then estimate. And then it's just standard evidence synthesis methods. You can combine methods where you know that the biases must be uncorrelated, so like a randomized trial and MR. Or here's a regression discontinuity. This was age when being able to leave school, which changed in the early 1970s, people used to be able to leave at 15, then 16 became the minimum school leaving age. UK Biobank, of which I'm a participant, overlaps that, so we can do a regression discontinuity. How do things change depending on whether you were born just before or just after that change? And what you see is that these are the Mendelian randomization and the raising of the school leaving age instrument associations. They're larger than the observational associations, and that's what you'd expect, because instrumental variables corrects for measurement error, takes all measurement error into account, and so you actually get the true causal effects are estimated from it. I was born just too late to be able to leave school at 15. If anyone had told me that the kids who then stayed on had to stay on until 16, if anyone at that time had told me it would ever have any beneficial effect, because it did on income and health behaviours and health, I thought the only reason these kids had to stay on was so they'd beat me up more. But it did. It had sizable effects. You can combine Mendelian randomization and negative controls. This is a sort of nonlinear Mendelian randomization analysis of BMI and mortality, which looks rather like the observational association in UK Biobank and Hunt. But the method, this particular Mendelian randomization method, is severely compromised. Reasons too complex to go into now here, but it's a severely compromised method. So what we did, when we thought this was unlikely to be true, so we did the MR study, but with age and sex as the outcome. Now, obviously, your BMI can't influence how old you are and your sex, but with this severely compromised method, sure enough, BMI makes you older and more male, which does tend to kill you. So, so you low BMI. So this is why you get high mortality at the low BMI part of the curve, and the same has been seen for studies on vitamin D, and many other nonlinear studies are severely compromised. So that's a nice use of negative controls, I think, to cast doubt on studies. Of course, there's lots of forms of data, that can't be just put into a sort of estimand. You can't just get an estimate of the causal effect, but it tells you that something is likely to be true. So, all forms of animal studies, cell systems, podocytes, interstitial fluid analysis, etc. All this thing feeds into what you know about what something might do. But this notion of biological plausibility, which is sadly just showing that something is biologically plausible, has rather little inferential power. I used to work on HIV many years ago, and at the time I was doing this, working in this area, a paper came out on male to female sexual transmission of HIV and the use of oral contraceptives. And one study suggested that oral contraceptives reduced the transmission, and they said that a direct effect on the genital mucosa, making it a less successful barrier to HIV, and immunosuppressive action, which would increase susceptibility to HIV. Sorry, so this is showing that oral contraceptive use increases the risk of future HIV infection. And you read that and you think, yeah, that sounds completely reasonable. Then coming out, so this is 1991, coming out the next week was a paper which showed the opposite. And then this said, progesterone containing oral contraceptives thicken cervical mucus, which might be expected to hamper the entry of HIV into the utero. That's, you think that sounds reasonable. So you can just get, if you find a finding and then you go and do Google Scholar searches, you can find something which will back it up. And just slapping that into your discussion isn't particularly useful. So there is work going on trying to actually use expert elicitation of priors about these forms of biological data in advance of the study being done. So I'm just going to finish with a crossword analogy for triangulation. So I think a triangulation can be thought of like a crossword, because these things are orthogonal. In a crossword, you have the ones going across and the ones going down. And so here we have a crossword saying the clue is convoluted, and you could have involved, confused, puzzling, tortuous, etc. You have various potential answers to that, so you're not going to write one of those in. But you see A and O, for instance. So what could that be? Sorry? Yeah, blood types, or it could be blood groups or blood types. Now, you have a couple of answers there, but you think that blood you're quite confident of, but then it could be group or type, so you just pencil one of them in. That's your A and O. And then you get gangster's girlfriend. Now, we all know that a gangster's girlfriend is a mole, don't we? We all watch those movies. And then anyone here from the sort of northeast? Anyone know what besom is? It's a broom. It's a broom. There you go. So, I was confident of that one. So that gives us an O. So that gets us down to confused or tortuous. You're only left with two possibilities. But it's blood group and mole which have given you that evidence. So these are things which don't actually intersect with the answer you want, but is strengthening your evidence for it. And then you have discharge of water, which is outflow. So this brings us down to think that it's tortuous. So you'd put tortuous in, but then you can confirm that, double acts is duos, and then is it blood group or blood type? It controls electricity, would be resistor, so it's blood group, not blood type. But you'd change it to type if you had another one. So the point of this is, as you put these answers in, some of them are just literally orthogonal to orthogonal to each other, and some are just don't even intersect. But together you build up a sort of strong foundation. I think that's with triangulation of evidence. It's evidence which is outside of the question that you're asking, but that can provide a firm scaffolding for it. There's enough for us, not that I can do it. This triangulation is similar to Bradford-Hill's criteria or viewpoints. He never called them criteria. The one issue with triangulation is rather like with the biological plausibility issue, is you really need to pre-register what you're going to do and make the data need to be open access and your code needs to be open access. Because if you pre-register something, you have to publish it. This is a natural experiment of when the National Heart, Lung and Blood Institute insisted on trials having to send in a report even if it wasn't published to NHLBI if they'd funded it. And this is just remarkable that suddenly all these studies that don't work come up. There's virtually none before this. No one published publishing negative trials. Of course, if you haven't pre-registered your protocol, you can analyze what's called p-hacking. You can just keep doing different analyses until you get the one which gives you the magic p-value, which will get you a New England Journal of Medicine paper. Or you could hypothesize after the results are known, harking. So that's why you do the analyses and then you get the hypothesis. Then you claim to have the hypothesis. It's the cognitive biases. If you've very committed to one particular answer. As I say, open access data is essential. In 1994, I wrote an editorial in the BMJ saying that papers submitted to journals had to be accompanied by a disk copy. Isn't that a nostalgic idea? Actually, a lot of you here are too young even to know what a disk copy was. Which was then sent to the statistical referees, could check the results, were not the product of over-enthusiastic data torture. And Richard Smith, who was the editor of the BMJ, and he liked this idea, and he took it to his editorial board, and it was voted on, and it got one vote, which was Richard Smith's vote. No one else would agree to do it. And you should make your code open access. You should pre-register what you're going to do. Here's one in the prenatal field, prenatal substance use that is underway. The consensus is related to what is admissible evidence, not to the findings. You have lots of consensus conferences that discuss findings on particular areas, but what you want to do is actually say what are the methods which we would actually trust in advance of knowing. And the potential limitations are gaming the system, or parking, which is pre-registration after the results are known. But that is fraud. That is essentially fraud. And I'm sure there's more. And these are the people I would want to thank. And there's a recent book, which has lots and lots of stuff on triangulation and of evidence, etc. Thanks very much.
Thanks very much. It's an excellent talk. We can have a couple of questions from the floor.
Hello, Carlos from University of Bristol. I'm going to apologize for the question first, but I think about Mendelian randomization more than I think I should. And I want to ask about the...
You need a copy of this book, honestly.
Which I work with Rebecca Richmond in a project about genetics. But the question is that the tension between a population and an individual level or Mendelian randomization. Just thinking, for instance, in a women with a GWAS showing they're prone to smoking, what would be the role for a smoking cessation treatment versus a population level intervention? Like I think it's New Zealand, we're going to try to forbid smoking for everyone to 2030. So it is quite deterministic to me, and I cannot figure out the answer for that question. I don't know if it makes sense.
So which do you think is deterministic? The Mendelian randomization?
The fact that if you have a specific GWAS profile, you can estimate even that if you're going to break our arm in the future.
So the point is these genetic effects for the individual level are tiny, absolutely tiny. That's why you need huge data sets. These things just change they change the probability, just very slightly. The Quina5 variant, which is really a large genetic effect, is essentially like the difference of a cigarette, less than a cigarette a day in terms of smoking. The difference in smoking levels is way above a cigarette a day. So you'd like doing a sort of trial where you're randomizing, you've got your two groups and they're different to a relatively small amount. All the other factors account for much more, but the same thing is true in a randomized trial of, say, blood pressure lowering. Say tablet lowers blood pressure by 5 or 6%. The fact of being randomized to a treatment explains about 2.5% of the variance in blood pressure in the population, or 2% of the variance in blood pressure in the population. But everyone takes those randomized trials as gold standard, which they are. So you can have relatively small differences, but they're free of confounding, which allows you to estimate the causal effect. But it's the antithesis of genetic determinism. It's saying the environment is all important. It's that the Mendelian randomization, paradoxically, it's that the best way you can actually find out about the environment is by using these genetic proxies, which account for rather small proportions of the variation in the population, but they generate differences which are not confounded, and for which there's obviously no reverse causation, which is probably often the most important thing in observational studies.
But that was, I put the example of weight management program or a smoking cessation individual program versus a policy that affects the entire population.
Yeah, well, no, I think that's sort of Jeffrey Rose's sick individual, sick populations notion, is that for many things, a population shift will lead to larger health benefits than will sort of finding the 5% with extreme values and doing something for them. So it's sort of shifting the risk distribution, just quite a slight shift of the risk distribution to the left, to the beneficial side, will lead to a large population difference.
Thank you. Fantastic talk, Chris Scaley, Imperial College London. You make a really elegant case for the importance of pre-registration of protocols for these kind of studies, but clearly that doesn't happen all the time, and journals don't force that like they do for trials. Do you think there's any possibility that might happen in the future?
So, it's been most successful for trials. and I mean, trials tend to have one or two hypotheses, etc. So it's easier to actually police for trials. I mean, even I think it's the New England Journal of Medicine held out for the longest, but even they now insist on pre-registration of trials. So it'd be difficult to get a trial published in a decent journal without pre-registration now. So the thing is, but of course, with observational data, you can just take every variable in UK Biobank, run it against everything, and find something to publish. It's much harder with observational analysis. I don't think you could never get straightforward, sensible pre-registration of just purely observational studies. But I think you can get pre-registration. So this is promoting pre-registration for triangulation of evidence, which I mean, I think journals should try to push for more studies actually using more than one method, and certainly there's some sort of interest in that. It's going to be a long process, but I think there's some movement in that direction.
Thank you.